So when we learned about the node voltage method, we learned that there were some kinds of circuits where we had to use this concept of a supernode in order to actually analyze them. And there's a similar concept for the mesh analysis method, which is called a supermesh. So I want to talk about these two cases so that we can recognize the pattern, and then we'll go on to explain how we deal with the idea of a supermesh. So just rewinding back to the node voltage method. Suppose I have a circuit like this one, then the way that I analyze it is going to depend a little bit on what's actually present in the circuit. So as an example, if I had a current source in the middle of this circuit, then let's think about the implications of how we would analyze this. So remember the node voltage method. The node voltage method uses Kirchhoff's current law. Okay, it uses KCL. So because we're using KCL, we're looking at the sum of currents. So therefore, current sources are easy to handle, right? Because if I know the current that's flowing into a node, then I can sort of draw all of my currents, and I can easily do KCL at this node V1 based upon the value of this current source. So there's some current, let's call it I1, that's generated by the source, and KCL is easy in this scenario. So we would just use a kind of normal standard node voltage method that you've practiced many times. If, however, I have the exact same circuit, but instead of putting a current source, I put a voltage source here. And we have a voltage VA that is generated by this particular voltage source. Then our problem becomes that writing KCL is now going to be difficult for this circuit. So writing KCL at node V1 is difficult. And why is that? It's because the current, let's call it IA, because the current generated by a voltage source, the current generated by a voltage source is not obvious, right? You have to actually do all the circuit analysis to figure out what that current is going to be. So we can't just sort of write down an expression for it in one step. And so we learned in a previous set of lectures that the way we address this problem is that we basically draw a box around our offending voltage source, and we call this thing a supernode. Supernode. And what we do is we write KCL for the entire supernode. So the solution, write KCL for the supernode as a whole. So we would look at all of the currents entering and leaving that supernode, and we would add them all up. And we know that that combination must equal 0 because the charge is conserved. So you can take any whole region of a circuit and write KCL, and it will still continue to apply. So that was the situation for nodal analysis, or the node voltage method as it's also called. So let's now consider the mesh current method using this same approach. So to remind ourselves, the mesh current method, uses Kirchhoff's voltage law, uses KVL. So we need to be able to calculate voltages sort of going around a loop, or around in our meshes. So because we're using KVL, if I had a voltage source here, VA, then it's fairly easy to write Kirchhoff's voltage law for each of the meshes in my circuit. So voltage sources are easy to handle since we can directly include them in the mesh equations. All right, so I can easily have a mesh, let's say this one here, IA, for example, and I do KVL around that mesh, and I just include the contribution of the two voltage sources. Okay, easy. Voltage sources are easy. However, suppose that I put a current source here, and let's think about that. Suppose I put a current source here. What happens now? So if I tried to write Kirchhoff's voltage law around this mesh, then I would need to know what is the voltage across the current source. So voltages across current sources are not obvious. And again, you have to pretty much solve the circuit in order to know what that voltage is actually going to be. So there's no simple expression that we can just write down for what that voltage across that current source is going to be. It actually depends upon the entire circuit. So every other component is going to influence what that voltage will be. And that's the whole point of trying to solve this circuit and analyze it. So the voltages across these current sources are not obvious. So as a result, current sources are hard to handle using the mesh current method. Now, I should point out this is only if you have a current source that is shared between two meshes. So this problem only arises because the current source here contributes to both meshes. If I had a different circuit, so current source and say a couple of meshes, and that was my layout, then it's fine, it's easy, because the current source here just tells me directly what my mesh current I1 is going to be. But if my current source is shared between two meshes, then what it does is it tells me the relationship between those mesh currents. So in particular, if I look at this circuit here, what I can tell by looking at this is that my current IA is going to be shared between I1 and I2. And if I look at the direction of the arrows, it will be minus I1 and a plus I2. So that's the meaning of the current source when you have these two separate meshes. However, I'm not able to write KVL around this mesh. For example, mesh 1, like I can't write KVL around that mesh because I don't know the voltage across the current source IA. So we don't know the voltage across the current source. So KVL at mesh I1 is not easy to write. I mean, we can write down, we can define a voltage, define a variable, but we can't really solve it. So the solution to this is the concept of a super mesh. So to define a super mesh, what I do is define a path that kind of cuts all the way around the offending current source. And I can call this thing here is the super mesh. And what I do is I write KVL around the entire super mesh. So I go all the way around the outside. And Kirchhoff's voltage law applies at any path through a circuit. So I can write KVL any path including this super mesh. So now I will generate an equation using the super mesh, and I also generate an equation by looking at the contribution of the mesh currents to the current source. So the highlighted there is one equation. Second equation is KVL around the super mesh. That gives me the two equations that I need to constrain the dynamics or define the dynamics of this particular system. So that's the relationship between supernodes and supermeshes. We can kind of summarize this behavior. So we have two methods. So we have a node voltage method, and the node voltage method uses Kirchhoff's current law. And so because it uses Kirchhoff's current law, it works well for current sources. So current sources are easy to work with. Voltage sources sometimes, it depends on the circuit, but sometimes difficult. And so that's where the concept of a supernode comes in. On the other hand, we also have mesh current method. And it works using Kirchhoff's voltage law. And because it uses Kirchhoff's voltage law, voltage sources are nice and easy. No matter what's the topology, if you've got voltage sources, they're easy to handle. But if you have current sources, then they can be sometimes difficult to use because we're not always able to know the voltage across a current source. And this difficulty arises because the voltage on the current source is hard to calculate, and the current through a voltage source is hard to calculate. And so that's why in these two cases, node voltage method and mesh current method sometimes become more difficult to use, and therefore we need this strategy of a super node and a super mesh to address this problem. So this is sometimes difficult, but not if we use, or we solve this challenge by using a super node, and over here the challenge is solved with using a super mesh. So that's the pattern or the relationship between these different problem solving strategies.